Imagine stepping into a spaceship tonight, punching in a single destination, and setting off toward a point in space exactly 1 light-year away. No stops, no detours, just you, the void, and the hum of the engine. How long do you think that trip would really take? If you're the kind of person who looks up at the night sky and wonders what's really out there, make sure to subscribe to this channel. Now let's get started. For a sense of scale, the Moon is about 384,000 kilometers from Earth. Light covers that distance in about 1.33 seconds. The Sun is about 150 million kilometers away, and light takes around 8 minutes to reach us from there. So when you look up at the Sun, you're technically seeing it as it looked 8 minutes ago, not as it is right now. Now take that same light and ask it to travel for an entire year without stopping. 9.5 trillion kilometers later, it finally arrives. That's the yardstick we're using today. And here's the twist: nothing we've ever built, and probably nothing we will build for a very long time, can move anywhere close to that speed. So let's bring this back to something we can actually picture. Let's talk about the fastest things humanity has ever made and see how they measure up. Right now, the fastest human-made object in history is NASA's Parker Solar Probe. This spacecraft is on a mission to fly incredibly close to the Sun, and to pull that off, it has to move fast enough to avoid falling straight into it. At its closest approach to our star, Parker Solar Probe reaches a jaw-dropping speed of about 690,000 kilometers per hour. That's roughly 191 kilometers every single second. To put that in perspective, at that speed you could travel from Los Angeles to New York in about 22 seconds. That sounds unbelievably fast, and it is by human standards. It's about 0.064% of the speed of light. Just a tiny fraction. And that's our fastest achievement ever in the history of our entire species. Now let's talk about the spacecraft that's actually gone the farthest. Voyager 1. Launched back in 1977, Voyager 1 has been cruising through space for nearly 5 decades. It used the gravity of Jupiter and Saturn to slingshot itself outward, and it eventually became the first human-made object to leave our solar system and enter interstellar space back in 2012. Today, Voyager 1 is more than 24 billion kilometers from Earth, and it's still moving outward at around 61,000 kilometers per hour. So here's the open loop I want to leave you with before we move into the math. If our fastest, most impressive machine takes 22 seconds to cross the entire United States, and our farthest traveled spacecraft has only covered a tiny sliver of a single light year in nearly 50 years, how long would it actually take either of them to cross that entire 9.5 trillion kilometer stretch? The answer is going to reframe how you think about distance in space, and honestly, it might change how you feel about your place in this universe. Stick around, because we're about to do the math together, and the number might genuinely surprise you. Let's start with Voyager 1, since it's the farthest traveled thing humanity has ever launched into space. Right now, it's cruising along at about 61,000 kilometers per hour. That's roughly 17 kilometers every second, which honestly sounds impressive until you compare it to the sheer size of a light year. If Voyager 1 kept moving at that exact speed, with no slowing down, no speeding up, just a straight steady cruise, it would take about 17,700 years to cover 1 light year. Let that sink in for a moment. 17,700 years. To put that into perspective, that's roughly 3 times longer than the entire span of recorded human history. The pyramids of Giza were built about 4,500 years ago, and that number is a mere blip compared to the journey we're talking about here. Now let's check in on Parker Solar Probe, our fastest machine. At 690,000 kilometers per hour, it would take approximately 1,564 years to travel the same distance That's better, sure, but it's still longer than the entire history of most nations on Earth today. You'd need generations upon generations of people living and dying aboard that spacecraft just to watch it complete a single light year. So here's a question worth sitting with. If our fastest technology still takes over 1,000 years just across a single light year, and the nearest star system to us, Alpha Centauri, is about 4.24 light years away, what does that actually mean for the dream of visiting another star? We'll get there, but first, I want you to really feel the weight of that number, because it changes how you look at every star in the night sky. Every single point of light you see up there isn't just far away. It's far away on a scale that our current technology genuinely cannot comprehend crossing within a human lifetime, or honestly, within dozens of human lifetimes strung together. This is actually a great moment to mention something. If the idea of speed limits in the universe has you curious about whether we could ever go faster, like actually approach or somehow beat the speed of light, I made an entire video exploring exactly that question. It's on the card above. It dives into concepts like warp drives, wormholes, and why Einstein's physics makes this so incredibly tricky. If today's video leaves you wanting more, that one is a perfect next stop. The link is in the description and pinned on the comments. Now let's push forward with a thought experiment, because raw numbers are one thing, but feeling them is another. Picture this. You board a spacecraft moving at Parker Solar Probe's blistering top speed. You leave Earth today. Your great-great-great-grandchildren, dozens of generations down the line, would be the ones who might finally arrive, assuming humans could even survive that long inside a metal tube hurtling through the emptiness of space. Entire civilizations could rise and fall on Earth in the time it takes that ship to complete its journey. Languages would evolve into something unrecognizable. Technology left behind would seem like ancient artifacts by the time news of arrival even made it back home, if it ever did. This is the brutal reality of interstellar distances. It's not that space is simply big. It's big in a way that makes our fastest achievements look almost trivial by comparison. And this is exactly why scientists and engineers have spent decades dreaming up entirely different ways to cross these distances, methods that don't rely on chemical rockets or gravity assists, but on physics we've barely begun to unlock. So let's talk about some of the theoretical propulsion methods that could shrink this timeline. Not science fiction fantasies, but real concepts that physicists and engineers have seriously studied. One idea is nuclear pulse propulsion, sometimes known by the name of an old research effort called Project Orion. The concept involves detonating small nuclear charges behind a spacecraft and riding the shockwave forward, kind of like surfing on a series of controlled explosions. Calculations from decades of research suggest a ship using this method could theoretically reach speeds up to around 10% the speed of light. That's still nowhere near light speed itself, but it's an enormous leap from anything we've built so far. At 10% the speed of light, a journey of 1 light year would take about 10 years. 10 years. Compare that to the 17,000 years we calculated for Voyager 1, and suddenly this idea sounds almost reasonable, but there's a catch, and there's always a catch in physics. Building a spacecraft that can survive repeated nuclear detonations behind it, while keeping a crew alive and protected from radiation, is an engineering nightmare that we haven't solved yet. It's theoretically possible according to the physics, but practically, we're still very far from making it a reality. Another concept getting serious attention today involves something called a light sail, most famously explored by the breakthrough Starshot initiative. The idea here is elegant. Instead of carrying fuel on board, you build an incredibly thin, lightweight sail, and you push it forward using powerful lasers fired from Earth. Since the spacecraft doesn't need to carry heavy propellant, it can be built extremely small and light, sometimes not much bigger than a smartphone chip attached to a sail just a few meters wide. Breakthrough Starshot has proposed that with a powerful enough laser array, a tiny probe like this could theoretically reach speeds of up to 20% the speed of light. At that pace, a 1 light-year journey would take only about 5 years, and reaching Alpha Centauri at 4.24 light-years away would take a little over 20 years. That's a mission that could realistically launch within someone's lifetime and actually report back results while they're still around to see it. Of course, this is still very much in the research and development phase. The laser technology required is nowhere near ready, and getting any meaningful data back from a probe that's small, moving that fast, past a star system that far away presents massive communication challenges of its own. But it's a genuinely promising direction, and it shows how thinking outside the box of traditional rocket propulsion could dramatically change these timelines we've been discussing. Here's the open loop I want to leave you with as we move forward. Even if we somehow reach 20% the speed of light, we're still talking about years, not days, to cross a single light year. So what happens to time itself once you start approaching those kinds of speeds? Does a year in space feel the same as a year on Earth? The answer involves one of the strangest and most mind-bending discoveries in all of physics, and it's going to completely reshape how you think about this entire journey. We're heading straight into Einstein's territory next, so get ready, because things are about to get delightfully weird. All right, here's where things get genuinely strange in the best possible way. So far, we've been talking about time from the perspective of someone standing still, watching a spacecraft zoom off into the distance. That's called the reference frame of an outside observer. But what if you were actually sitting inside that spacecraft, looking out the window? According to Einstein's theory of special relativity, your experience of time would be noticeably different. This phenomenon is called time dilation, and it's one of the most well-tested, well-confirmed ideas in all of physics. It states that the faster you move relative to something else, the slower time passes for you compared to that other thing, not because your watch is broken, and not because you're imagining it. Time itself, quite literally, moves at a different rate for you. Let's put a number on this. If you were traveling at 20% the speed of light, the speed we mentioned with that theoretical light sail concept, the effects of time dilation would still be pretty small, only slowing your clock down by about 2% compared to someone back on Earth. Noticeable to precise instruments, but not exactly a dramatic sci-fi movie moment, but push that speed higher, say to 90% the speed of light, and things start to shift in a big way. At that speed, time for you would slow down to less than half the rate experienced by people back home. Push it even further to 99% the speed of light, and for every year that passes for you on board the ship, about 7 years would pass back on Earth. Get even closer to light speed, say 99.9%, and that ratio jumps to about 22 years passing on Earth for every single year you experience on board. This isn't science fiction. This effect has actually been measured directly, using incredibly precise atomic clocks flown on airplanes and observed constantly in particle accelerators here on Earth, where subatomic particles moving near light speed literally last longer, from our perspective, than physics would otherwise predict. It's also been confirmed through astronauts on the International Space Station who experience a tiny amount of time dilation from their orbital speed, ending up microseconds younger than people on Earth after long missions. Small effect, but real, measured, and repeatedly confirmed. So here's where this connects back to our light-year journey. If you built a spacecraft capable of reaching somewhere close to the speed of light, and I mean genuinely close, like 99.9%, the trip that looks like it takes over a year from Earth's perspective could feel like just a matter of weeks or months to you, the traveler on board. From your point of view, sitting in the ship, distances actually appear to shrink too, thanks to a related effect called length contraction. The universe, from your seat, would look like it's squishing itself smaller in the direction you're traveling. This means that theoretically, if humanity ever built engines capable of sustaining speeds extremely close to light speed, a person could cross vast cosmic distances within their own lifetime, even if, from Earth's perspective, centuries or millennia ticked by during that same trip. It's a genuinely mind-bending trade-off. You could travel to distant stars in what feels like a short journey to you, but you'd return to an Earth that has aged far beyond anything you'd recognize. Everyone you knew, gone. Technology, unrecognizable. Culture, transformed. It's essentially one-way time travel into the future, dressed up as a road trip through space. Here's the catch, though, and it's a big one. Getting a spacecraft anywhere near that speed requires an amount of energy that borders on the absurd. As an object approaches the speed of light, its effective mass, in terms of how much energy it takes to keep accelerating it, increases dramatically. Physicists call this relativistic mass increase, and it means that as you get closer and closer to light speed, you need exponentially more energy for each tiny increase in velocity. Getting all the way to light speed itself would require infinite energy, which is exactly why physics tells us it's impossible for anything with mass to actually reach that speed. Light itself is different because photons have no mass, which is part of why they're allowed to move at that ultimate cosmic speed limit. So even in our wildest, most optimistic scenarios of futuristic engines, hitting something like 99%, the speed of light would require energy sources we simply don't have any blueprint for yet. We're talking about power outputs that dwarf anything humanity currently produces, harnessed in a way that could be safely used for propulsion without destroying the ship or its crew. This brings up a fascinating open question that scientists actively debate today. Some researchers look at concepts like nuclear fusion propulsion, where you'd fuse hydrogen into helium on board the ship, similar to the reaction that powers the sun, as a potential energy source strong enough to get meaningfully closer to these relativistic speeds. Fusion offers an enormous amount of energy from a relatively small amount of fuel, and unlike fission, it doesn't produce nearly as much dangerous radioactive waste. The challenge is that humanity still hasn't achieved sustained controlled fusion that produces more energy than it consumes, even here on Earth in stationary laboratory conditions. We're getting closer, with facilities like the National Ignition Facility achieving what's called fusion ignition in 2022, but turning that into a compact, reliable propulsion system for a spacecraft is still a challenge for future generations of engineers and physicists to solve. There's also ongoing scientific debate about whether we might one day discover entirely new physics that could offer shortcuts around these speed limitations altogether, rather than simply building faster rockets. Concepts like the Alcubierre warp drive, first proposed by physicist Miguel Alcubierre back in 1994, suggest that instead of moving through space faster than light, you might be able to warp space itself around a ship, contracting space in front of it and expanding space behind it. In theory, this could allow effective faster-than-light travel without violating relativity, since the ship itself wouldn't be moving faster than light locally. It's the space around it that's doing the moving. This concept remains purely theoretical, and it requires forms of energy and matter that we don't currently know how to produce or even confirm exist in the way the math requires. But it represents exactly the kind of open-minded, boundary-pushing thinking that keeps physicists exploring new possibilities rather than assuming our current limitations are permanent. And again, if this kind of faster-than-light concept fascinates you, that's precisely the territory covered in much more depth in my video, what it would take to travel faster than light, which pairs really well with everything we're covering here. So let's bring this back down to something a little more grounded, because relativity is fascinating, but it's also a bit of a rabbit hole that takes us away from realistic near-future possibilities. Let's ask a different question. Given everything we actually know how to build today, or are seriously developing right now, what's the most realistic timeline for reaching another star system? Not a light year of empty space, but an actual destination like the nearest star system to our own. That's where we're headed next, and the numbers might surprise you in a different way than you'd expect. Let's ground ourselves back in reality for a moment, because as fun as warp drives and relativistic starships are to imagine, they're still firmly in the realm of theory. So let's ask a more practical question. Using technology that's either already built, currently being developed, or seriously proposed by real scientific teams, how long would it realistically take us to reach a star system that's about 1 light-year's worth of distance away, give or take? The nearest star system to our own is Alpha Centauri, a triple-star system located about 4.24 light-years from Earth. That's a little more than 4 times the distance we've been discussing throughout this video, but it gives us a real destination to attach these numbers to, rather than just an abstract point in empty space. Remember the breakthrough Starshot project we touched on earlier. This is actually one of the most seriously funded and researched attempts at interstellar travel happening right now. The project was announced back in 2016, backed by physicist Stephen Hawking and billionaire investor Yuri Milner, among others. The concept involves building an array of powerful ground-based lasers that would fire a coordinated beam at a small spacecraft equipped with an ultra-thin reflective sail. The idea is that the light itself, its sheer photon pressure, would push the sail and accelerate the tiny probe attached to it, called a starship, up to speeds approaching 20% the speed of light within just a few minutes of firing. If this technology matures the way its creators hope, a mission to Alpha Centauri using this method could take around 20 to 25 years to arrive, followed by another 4 years or so for any data or images it captures to travel back to Earth at the speed of light. That means the entire round trip from launch to receiving data back home could realistically take around 25 to 30 years. That's genuinely within a human lifetime. That's a project someone could start as a young scientist and see completed before retirement. However, and this is an important however, the technology required for breakthrough Starshot doesn't fully exist yet. The lasers needed would require power levels far beyond what we currently produce in a coordinated, precisely targeted array. The materials for the sail need to be almost impossibly thin while still surviving the intense heat and radiation of being blasted by a laser powerful enough to accelerate it to relativistic speeds. And communicating with a device that's small, that far away, moving that fast presents a genuinely difficult engineering puzzle. As of now, this remains an active area of research rather than a mission with a confirmed launch date. So let's look at another approach, one that trades speed for practicality, the idea of a generation ship. This concept has been discussed by scientists and science fiction writers alike for decades, and it's exactly what it sounds like. Instead of trying to get somewhere quickly, you build a massive, self-sustaining spacecraft, essentially a small traveling world, capable of supporting multiple generations of humans living, growing up, and eventually dying on board, all before the ship reaches its destination. Using currently plausible propulsion methods like advanced ion engines or nuclear thermal propulsion, calculations suggest a generation ship might travel at speeds around 1 to 2% the speed of light. At that pace, reaching Alpha Centauri would take somewhere between 200 and 400 years. That means the great-great-great-grandchildren of whoever boards that ship at launch would be the ones who finally step onto a new world, having never known Earth themselves, having been born, raised, and having lived their entire lives inside that traveling vessel. This raises fascinating questions that go beyond pure physics and drift into biology, sociology, and even philosophy. Could a closed ecosystem sustain human life for centuries without any outside resupply? Could human culture and social structures remain stable across that many generations, isolated from the rest of humanity, in the vacuum of space? These aren't questions physics alone can answer, and they highlight just how much interstellar travel is a challenge that spans every branch of science, not just rocketry and engines. There's also a lesser-known concept worth mentioning here called nuclear thermal propulsion, something NASA and other space agencies have actually tested in various forms since the 1960s. Instead of burning chemical fuel like a traditional rocket, nuclear thermal engines use a nuclear reactor to superheat a propellant like hydrogen and expel it out the back at extremely high speeds, generating far more efficient thrust than conventional chemical rockets. NASA has actually been developing modern versions of this technology through partnerships like the Draco program, aimed initially at cutting travel time to Mars, not interstellar destinations, but it represents a real, functioning stepping stone toward more advanced propulsion methods that could eventually be scaled up for much longer journeys. Even with these improvements, nuclear thermal propulsion alone wouldn't get us anywhere close to a meaningful fraction of light speed. It's better suited for cutting the travel time to places like Mars from several months down to potentially just a few weeks. That's an enormous improvement for exploring our own solar system, but it doesn't move the needle much when we're talking about crossing entire light years to reach another star. So here's an interesting open loop worth considering. If our most advanced realistic propulsion concepts today can only get us to Alpha Centauri within a few hundred years at best, using generation ships, or theoretically within a human lifetime, using something as ambitious and unproven as laser sail technology, what does that actually tell us about humanity's odds of becoming a truly interstellar species anytime soon? Is this a problem that will take centuries of technological development to solve, or is there a breakthrough discovery waiting just around the corner that could change everything overnight? To answer that, we need to zoom out a bit and think bigger. Not just about propulsion, but about the actual physics of the universe itself, and whether there are loopholes we haven't fully explored yet. That's exactly where we're headed next, as we look at some of the more speculative, but scientifically grounded, ideas that researchers are actively investigating today. Let's talk about wormholes for a moment, because this is where physics starts to sound like science fiction, even though the underlying mathematics comes from very real, peer-reviewed general relativity. A wormhole, technically called an Einstein-Rosen bridge, named after Albert Einstein and physicist Nathan Rosen, who described the concept mathematically back in 1935, is essentially a theoretical tunnel connecting two separate points in space-time. Imagine folding a piece of paper in half and poking a hole through both layers with a pencil. Instead of traveling across the flat surface of the paper, that pencil hole gives you a shortcut straight through. That's the basic idea behind a wormhole, a shortcut through the fabric of space itself, rather than traveling across the normal distance between 2 points. If wormholes actually exist, and more importantly, If they could somehow be stabilized and made safe enough to travel through, they could theoretically let you cross a light year, or honestly thousands of light years, in a fraction of the time it would take at even the fastest speeds we've discussed so far. You wouldn't be breaking the speed of light rule because you wouldn't actually be traveling through normal space at all. You'd be taking a shortcut around it entirely. Here's the important scientific caveat though. As of today, no wormhole has ever been observed, detected, or confirmed to exist anywhere in the universe. They remain a mathematically valid solution within Einstein's equations of general relativity, meaning the math allows for them to exist, but that doesn't automatically mean nature has actually built any. Physicists like Kip Thorne, who won the Nobel Prize in Physics in 2017 for his work on gravitational waves, have done serious research into what it would theoretically take to keep a wormhole open and stable enough for something or someone to pass through it safely. The problem is that the math suggests you'd need something called exotic matter, material with negative energy density, to hold a wormhole open and prevent it from collapsing in on itself instantly. And here's the thing, we've never confirmed that negative energy density matter at the scale required actually exists in a usable form anywhere in nature. There are some genuinely fascinating quantum phenomena, like the Casimir effect, which does produce a tiny measurable amount of negative energy density under very specific laboratory conditions, but scaling that up to wormhole-sized requirements is, as far as we currently understand physics, a challenge that might not even be theoretically possible, let alone practically achievable. So while wormholes remain a legitimate topic of serious academic research and mathematical exploration, they currently exist purely as the math says it's a loud concept, not an we have evidence this is real concept. It's important to be honest about that distinction, because it separates genuine cutting-edge physics from science fiction speculation, even though the line between the two can sometimes feel thin and exciting to explore. Now let's pivot to something equally strange, but grounded in phenomena we've actually observed and measured directly in laboratories: quantum entanglement. Quantum entanglement is a real, well-documented phenomenon where two particles become linked in such a way that measuring the state of one instantly correlates with the state of the other, regardless of the distance separating them. Einstein famously called this spooky action at a distance, and honestly, that nickname captures the feeling of it perfectly. Experiments have confirmed entanglement across distances of over 1,200 kilometers using satellites like China's Messias, launched back in 2016, which successfully demonstrated entangled photon pairs being distributed between ground stations separated by that distance. Here's where I need to be very clear and scientifically honest, because this is a common misconception that even shows up in some popular science content. Quantum entanglement does not allow for faster-than-light communication or travel. This is a critical point that physicists have repeatedly confirmed. While the correlation between entangled particles does appear instantaneously, you cannot use this phenomenon to send actual information faster than light. This limitation is formally described by something called the no communication theorem, and it's been consistently supported by every experiment conducted so far. So, while entanglement is genuinely one of the strangest, most fascinating confirmed phenomena in modern physics, and it does have real, practical applications in fields like quantum computing and quantum cryptography, it unfortunately does not offer a shortcut for physically traveling across a light year of distance, or for sending a message across that distance instantly. It's a beautiful piece of the quantum puzzle, but it's not the interstellar travel solution some people hope it might be. This brings us to an honest, important moment in our exploration today. As of our current scientific understanding, there is no confirmed proven shortcut around the vast distances of space, no wormhole we've detected, no quantum trick that breaks the light speed barrier, no loophole we've verified through actual observation. What we have are incredibly fast, but still fundamentally limited propulsion concepts and theoretical frameworks like wormholes that remain mathematically permitted but entirely unconfirmed by evidence. And you know what? I actually find that reassuring. In a strange way, it means the universe still holds genuine mysteries worth pursuing. It means there's real, meaningful scientific work left to do, real questions left unanswered, and real discoveries waiting for the next generation of physicists, engineers, and curious minds, maybe even someone watching this video right now, to uncover. So let's take a step back from propulsion and physics for a moment, and instead ask a slightly different, more philosophical question. If crossing even a single light year takes anywhere from thousands of years using current technology, down to potentially a couple of decades using speculative near-future tech, what does that tell us about our actual place within the broader universe? How does this distance challenge, or maybe even change, how we think about our future as a species? That's where we're heading next, and I think you're going to find this next section genuinely moving. So here's a thought I want to sit with for a moment, because I think it's easy to rush past the emotional weight of everything we've just covered and jump straight to the next cool fact. Let's just pause and really absorb what it means that even something as seemingly modest as 1 light year, a distance that sounds almost graspable when you first hear the term, translates into thousands of years of travel using anything we can actually build today. It means that, in a very real sense, we are isolated, not by choice, not because of some cosmic punishment, but simply because of the scale of the universe we happen to live in. Earth isn't just a planet floating in space, it's an island separated from its nearest neighboring star systems by distances so vast that even light, the fastest thing in existence, takes years to cross them, and we, bound by mass, by fuel, by the physical limitations of engines and materials, are separated by distances that would take generations, sometimes hundreds of generations, to cross using anything currently within our grasp. But here's the flip side of that isolation, and I think it's actually the more important point. This same vastness is exactly what makes our little corner of the universe feel so remarkable. Earth isn't just some random rock we happen to be standing on. It's the only place, out of an almost incomprehensibly large number of possibilities, where we know for certain that life managed to take hold, evolve, develop consciousness, and eventually build civilizations capable of asking questions like the ones we're exploring in this very video. That's not something to feel small about. That's something to feel genuinely amazed by. Think about the sheer improbability stacked on top of improbability that had to occur for you to even be here right now, watching this, thinking about these ideas. Our planet had to form at the right distance from the right kind of star. It had to develop a stable atmosphere, liquid water, the right chemical building blocks, protection from harmful radiation through a magnetic field, and billions of years of relatively stable conditions, allowing evolution to slowly, patiently, build up the complexity required to produce a species capable of building telescopes, launching probes, and calculating exactly how long it would take to reach another star. And when you place that reality against the emptiness and scale of interstellar space that we've spent this entire video exploring, it reframes the conversation entirely. Suddenly, the question isn't just how do we get somewhere else? It becomes how extraordinary is it that we're even here, capable of asking this question in the first place? That shift in perspective, from feeling small and isolated to feeling genuinely fortunate and remarkable, is honestly one of the most valuable things that studying astronomy and physics can offer anyone. This is actually one of the reasons scientists take the search for other life so seriously, even knowing how astronomically difficult interstellar travel currently is. Projects like the Search for Extraterrestrial Intelligence, known as SETI, and newer efforts like the Breakthrough Listen initiative, which has been scanning the skies since 2015 using radio telescopes to search for signals from other potentially intelligent civilizations, aren't necessarily expecting to find a neighbor we could easily visit. They're motivated by a much deeper question. Are we alone? And if we're not, what does it mean that, even if other intelligent life exists somewhere out there, the sheer physical distance separating us might make actual contact, let alone travel, functionally impossible for both sides, at least using anything resembling current technology? This ties into something called the Fermi paradox, a concept named after physicist Enrico Fermi, who reportedly posed a simple but profound question back in 1950. Given the sheer number of stars and potentially habitable planets in our galaxy alone, and given how old the universe is, shouldn't we have encountered some evidence of other intelligent civilizations by now? Where is everybody? One of the most compelling proposed explanations for this paradox directly connects to everything we've discussed today. Maybe intelligent civilizations are out there, plenty of them even, but the distances between stars are so enormous and the energy requirements for meaningful interstellar travel or communication so extreme that most civilizations simply never develop the technology needed to reach each other or even detect each other's signals clearly before either running out of time, resources, or simply losing interest across the ridiculously long timescales involved. It's not that we're necessarily alone. It might just be that space itself is doing an extremely good job of keeping everyone separated. That's a genuinely humbling thought, but I'd argue it's not a discouraging one. If anything, it makes the effort we're currently putting into projects like Breakthrough Starshot, nuclear thermal propulsion research, and even purely theoretical work on things like wormhole physics all the more meaningful. Every incremental step forward, every improvement in propulsion efficiency, every new theoretical framework explored chips away, even just slightly, at the barrier that separates us from potentially answering some of the biggest questions humanity has ever asked. So with that bigger picture in mind, let's bring this back to something a little more tangible and forward-looking. Given everything we've covered, the current technology, the near-future possibilities, and the purely theoretical concepts still waiting for real breakthroughs, what would an actual, realistic timeline for humanity's interstellar future actually look like? Not what could theoretically happen, but a grounded, honest exploration of where the science and engineering communities genuinely believe we're headed over the coming decades and centuries. That's exactly what we're going to break down next. All right, let's get practical for a moment and actually sketch out a realistic timeline. Not science fiction speculation, but a grounded look at what serious scientists, space agencies, and aerospace engineers actually believe is achievable, and roughly when, based on where the technology stands today and the pace of current research. Let's start close to home, because that's genuinely where this journey begins. Right now, in the near term, meaning the next 10 to 20 years, the realistic focus isn't interstellar travel at all. It's about mastering our own solar system more efficiently. NASA's Artemis program, aimed at returning humans to the moon and eventually establishing a sustained presence there, is meant to serve as a testing ground for technologies that will eventually matter for much longer journeys, things like closed-loop life support systems, in-situ resource utilization, meaning using materials found on other worlds rather than hauling everything from Earth, and radiation shielding for long-duration spaceflight. Around that same time frame, missions to Mars whether robotic or eventually crewed, will likely benefit from nuclear thermal propulsion systems like the ones being developed under NASA's Draco program, which we touched on earlier. If successful, these engines could cut travel time to Mars significantly, and more importantly, they'll give engineers real-world data on how nuclear propulsion systems perform outside a laboratory, data that's essential before anyone seriously considers scaling this technology up for anything resembling interstellar distances moving into the medium term, let's say somewhere between 20 and 50 years from now. This is roughly where projects like Breakthrough Starshot become genuinely relevant, assuming the underlying technology matures as researchers hope. This window is when we might realistically expect the first serious attempt at sending a small, unmanned probe toward Alpha Centauri using laser sail propulsion, assuming the necessary laser array, incredibly thin sail materials, and miniaturized sensor technology all reach the required level of sophistication. That's a big assumption, admittedly, but it's not an unreasonable one given the pace of advancement we've seen in materials science and laser technology over just the past few decades. This timeframe is also when concepts like fusion propulsion might start moving from theoretical models into actual prototype testing. Fusion, the same process that powers our sun, has been the subject of serious research for decades, most notably through projects like the International Thermonuclear Experimental Reactor, known as ITER, currently under construction in France, which aims to demonstrate that fusion can produce more energy than it consumes. Something researchers have been chasing since experiments began there in the 2010s. If fusion technology eventually becomes practical and controllable enough for propulsion purposes, rather than just power generation, it could offer a genuinely significant leap forward in propulsion efficiency, potentially pushing achievable speeds well beyond what chemical or even nuclear thermal rockets could ever manage. If you are enjoying this journey, please subscribe to this channel. You will be part of a community who explores the cosmos together. Now let's push further out into what we might call the long term, roughly 50 to 200 years from now. This is the realistic window when a generation ship, the kind we discussed earlier, might actually become buildable, assuming humanity continues developing closed-loop ecological systems, advanced radiation shielding, and propulsion technology capable of sustaining a percent or two of light speed over an extended journey. It's also the time frame when we might see the first meaningful expansion of permanent human settlements beyond Earth and the Moon, potentially including Mars, and possibly some of the more promising moons in our own solar system, like Europa or Enceladus, both of which show tantalizing evidence of subsurface oceans that could potentially support microbial life and which serve as valuable testing grounds for the kind of self-sufficient habitats that would eventually be needed for a true interstellar generation ship. And then there's the far future, the truly speculative territory beyond 200 years from now, where genuinely transformative breakthroughs would need to occur for interstellar travel to become anything resembling routine. This is where concepts like the Alcubierre warp drive we discussed earlier, or a confirmed, stabilized wormhole, or some entirely new physics we haven't even theorized yet, would need to move from mathematical possibility into engineered reality. Nobody, including the most optimistic physicists working in these fields today, can honestly predict whether that will take another 200 years, 2,000 years, or whether it will simply never happen at all, because the underlying physics genuinely doesn't allow for it. I think it's worth being honest about that uncertainty, rather than pretending we have it all figured out. Real science, real exploration, thrives on that kind of honesty. We don't know everything yet, and that's not a weakness. That's the entire reason discovery still matters. the entire reason there's still meaningful work left for future scientists, engineers, and curious minds to pursue. So here's a question worth carrying forward as we continue. Given this realistic timeline, spanning from practical near-term solar system technology all the way out to speculative far-future physics, where do you think humanity's greatest opportunity actually lies? Is it in patiently building up incremental improvements over centuries, generation ship style? Or is it in chasing that one transformative breakthrough that could change everything overnight, the way splitting the atom or discovering general relativity once did? That question actually leads us perfectly into our next section, where we're going to explore some of the most promising, currently active research projects working on exactly this problem, and what their own scientists and engineers are saying about their realistic hopes and expectations. Let's get specific now and talk about actual currently active research projects, the real teams of scientists and engineers who are working right now, today, on pieces of this exact puzzle. Because I think it's easy to talk about interstellar travel in abstract terms, but it becomes a lot more compelling and honestly a lot more grounded when you realize there are actual funded programs, actual published papers, and actual working prototypes moving this field forward, step by step. Let's start with breakthrough Starshot, since we've referenced it a few times already. This project was launched back in 2016, backed by the Breakthrough Initiatives organization, which was founded by the late physicist Stephen Hawking, along with entrepreneur Yuri Milner and Facebook founder Mark Zuckerberg. The goal is genuinely ambitious: develop a fleet of tiny, gram-scale spacecraft called starships attached to ultra-thin light sails, and accelerate them using a massive ground-based laser array to roughly 20% the speed of light, fast enough to reach Alpha Centauri in about 20 years rather than tens of thousands. As of the most recent updates from the project, researchers have been focused on solving some genuinely difficult engineering problems. Things like developing sail materials that can survive the intense heat and pressure of a laser beam powerful enough to achieve that kind of acceleration without simply melting or tearing apart. They've also been working on miniaturizing the electronics needed for the starship itself, since it needs to carry cameras, communication equipment, and power systems, all within a device roughly the size of a postage stamp. The project has stated that full-scale implementation is likely still decades away, but they've made real, publishable progress on sail material science and laser array design in the years since the initiative launched. Next, let's talk about NASA's DRACO program, which stands for Demonstration Rocket for Agile Cislunar Operations. This is a joint effort between NASA and DARPA, the Defense Advanced Research Projects Agency, aimed at demonstrating a functioning nuclear thermal rocket engine in actual orbit. As of recent updates, the program has been targeting a demonstration mission, with the engine itself being developed by Lockheed Martin in partnership with BWX Technologies for the nuclear reactor component. If this demonstration succeeds, it would represent the first time a nuclear thermal engine has operated in space since the 1970s, when similar concepts were tested on the ground but never flown. Then there's fusion research, which, while not exclusively focused on propulsion, represents some of the most important underlying science that future interstellar concepts will likely depend on. ITER, the International Thermonuclear Experimental Reactor project we mentioned earlier, has faced its share of delays and cost overruns since construction began, which is honestly fairly typical for a project of this scale and ambition, but it remains the largest, most internationally collaborative fusion experiment ever attempted, involving 35 countries working together. Separately, private companies like Commonwealth Fusion Systems and Helion Energy have been pursuing their own fusion approaches, with Helion notably securing an agreement with Microsoft for future fusion-generated electricity, signaling that serious commercial interest in fusion technology is growing well beyond government-funded research alone. I want to be honest with you about something important here, though. None of these projects, Starshot, Draco, ITER, or any private fusion venture, are explicitly designed as complete interstellar travel solutions on their own. They're each solving individual pieces of an enormously complex puzzle. Starshot focuses on propulsion for tiny probes, not human transport. Draco focuses on nuclear thermal propulsion for solar system travel, not interstellar distances. Fusion research focuses primarily on energy generation, with propulsion applications still largely theoretical, but that's actually exactly how transformative technology tends to develop throughout history. The Apollo program didn't invent every piece of technology needed for the moon landing from scratch. It built upon decades of prior research in rocketry, computing, materials science, and life support systems, each developed somewhat independently, then eventually combined into something extraordinary. It's entirely reasonable to expect that humanity's eventual interstellar propulsion breakthrough, whenever and however it finally happens, will similarly emerge from combining insights across multiple currently separate fields of research, rather than from any single dramatic invention. So when you ask experts directly, and there have been surveys and panel discussions among aerospace engineers and physicists on exactly this topic, the general consensus tends to be cautiously optimistic, but genuinely honest about the scale of the challenge. Most agree that some kind of robotic interstellar probe launch, likely using laser sail technology similar to Starshot, is plausible within the next 50 to 100 years. Human interstellar travel, however, using a generation ship or similarly advanced concept, is generally considered a much longer-term goal, likely a century or more beyond that, assuming no unexpected breakthrough dramatically accelerates the timeline. Given all of that, I think it's worth pausing here and asking ourselves something a little different. Instead of just asking, when will we get there, maybe the more interesting question is, what would it actually take, in terms of global cooperation, funding, and sustained scientific commitment, to make any of this happen within our lifetimes or within our children's lifetimes? Because the honest truth is that the physics and engineering challenges, while genuinely difficult, might actually be more solvable than the human challenges of sustained funding, international collaboration, and long-term societal commitment required to see projects like these through to completion. That's actually a perfect place to shift our focus in the next section, where we're going to explore exactly that, the human and societal side of interstellar ambition, and what it would realistically take for humanity to commit to this kind of multi-generational effort. Let's shift gears now and talk about something that doesn't get nearly enough attention in most discussions about interstellar travel, the human side of the equation. Because honestly, Josue, I'd argue that the sociological and political challenges facing humanity's interstellar ambitions might actually be tougher than the physics itself. And that's saying something given everything we've covered so far. Think about what it would actually take, in practical terms, to fund and sustain a project spanning decades, or in the case of a generation ship, potentially centuries. We're not just talking about a large budget, although that's certainly part of it. We're talking about sustained political will across multiple generations of leadership, across changing economic conditions, shifting public priorities, and probably multiple wars, recessions, and unexpected global crises along the way. Think about how differently the world looked just 20 or 30 years ago, and then imagine trying to maintain a consistent, well-funded, multi-century commitment to a single scientific goal, despite all of that unpredictability. Historically, we do have some precedent for this kind of long-term thinking, even if it's admittedly rare. Cathedrals in medieval Europe sometimes took over a century to complete, with entire generations of builders working on projects they knew they'd never personally see finished. The construction of the Great Wall of China spanned multiple dynasties over roughly 2,000 years. These examples show that humans are capable of sustained multi-generational commitment to enormous projects, but they also show that this kind of commitment typically requires powerful cultural or religious motivation, centralized authority, and often, frankly, significant amounts of forced labor or resource extraction that wouldn't be acceptable or practical in a modern context. So the real question becomes, what would motivate modern humanity? Spread across nearly 200 different nations with wildly different governments, economic systems, and cultural values, to commit to something on this scale voluntarily. International collaboration on massive scientific projects isn't unprecedented. The International Space Station stands as a genuinely remarkable example of nations that were often geopolitical rivals working together successfully for decades. CERN, the European Organization for Nuclear Research, is another great example, bringing together scientists from dozens of countries to operate the Large Hadron Collider and pursue fundamental physics research that benefits humanity as a whole rather than any single nation. But scaling that kind of cooperation up to the level required for a genuine interstellar program, one that might require sustained investment across multiple centuries, is an entirely different challenge. It would likely require some combination of things we don't currently have in sufficient supply, meaning a shared sense of species-level identity that transcends national boundaries, economic systems capable of directing enormous resources toward long-term speculative goals rather than short-term returns, and probably some kind of triggering event or shared realization that makes interstellar expansion feel not just interesting, but genuinely necessary. That last point is actually something serious researchers and philosophers have written about. The concept of humanity as a single planet species being inherently vulnerable to extinction-level events, whether that's a large asteroid impact, a supervolcanic eruption, or some other global catastrophe, has been used by prominent scientists, including the late Stephen Hawking, as an argument for why expanding beyond Earth isn't just an exciting scientific goal, but potentially a survival imperative for our species as a whole. Hawking specifically argued on several occasions that humanity needed to become a multi-planetary and eventually multi-stellar species within the next few hundred years if we wanted to guarantee our long-term survival, given the various existential risks we face by remaining confined to a single planet. Whether or not you find that argument convincing, and reasonable people certainly disagree about how urgent that risk actually is, it does represent one of the more compelling motivational frameworks that could theoretically sustain interstellar ambition across generations. The idea that this isn't just about curiosity or exploration for its own sake, but about ensuring humanity has a future at all, regardless of what happens to Earth specifically. There's also a slightly less dramatic but equally important motivational factor worth mentioning, and that's simple economic incentive. As private companies increasingly enter the space industry, and as asteroid mining, off-world manufacturing, and eventually interstellar resource acquisition become theoretically profitable ventures, market forces themselves might end up driving investment into exactly the kind of propulsion and life support technology needed for interstellar travel without requiring the same level of centralized government commitment that pure scientific curiosity alone might demand. We've already seen this play out to some degree with companies like SpaceX dramatically reducing the cost of orbital launches through reusable rocket technology, something that seemed almost impossibly ambitious when Elon Musk first proposed it, yet has become genuinely routine within just the past decade. So when you put all of this together, Josue, I think the honest conclusion is that humanity's interstellar future depends on a combination of factors that go well beyond pure physics and engineering. It depends on sustained international cooperation, a compelling shared motivation, whether that's survival, curiosity, profit, or some combination of all three, and probably a fair amount of luck in terms of avoiding the kinds of global catastrophes or prolonged conflicts that could derail long-term scientific investment for generations at a time. That brings us, finally, to where I want to wrap up this entire exploration, pulling together everything we've covered, from the raw physics of distance and speed, through the wildly creative propulsion concepts still being researched today, all the way to this final deeply human question of whether we actually have what it takes as a species to commit to this journey at all. Now let's slow down and actually sit with the physics of relativity a little longer, because I don't think we've fully unpacked just how strange and counterintuitive time dilation really becomes once you push speeds toward a meaningful fraction of light speed. This deserves its own dedicated space. Here's the core idea, stated as plainly as I can. Einstein's special relativity tells us that time doesn't pass at the same rate for everyone. It depends on your velocity relative to something else. The faster you move, the slower time passes for you, relative to someone who stayed still. This isn't some abstract mathematical trick, it's been experimentally confirmed repeatedly, most famously through experiments involving atomic clocks flown on airplanes, and continuously through the tiny but measurable time discrepancies experienced by GPS satellites, which have to be corrected for exactly this effect to keep our navigation systems accurate. Now, scale that effect up to something like 80 or 90% the speed of light, and the implications become genuinely mind-bending. Let's go back to our light-year example, but let's actually run the numbers this time, because I think seeing the actual math makes this land differently than just talking about it abstractly. Say a spacecraft travels at 90% the speed of light, covering a 1 light-year distance. The time dilation factor, calculated using the Lorentz transformation, works out to roughly 2.29. That means for every year that passes for an observer back on Earth, only about 5.5 months pass for the crew aboard that spacecraft. So while Earth-based observers would calculate the trip taking a little over 1 year, the astronauts themselves would experience it as considerably shorter, closer to 5 or 6 months of subjective time. Plill that further to say 99% the speed of light, and the dilation factor jumps to about 7. Suddenly, a journey that takes just over a year from Earth's perspective would feel like less than 2 months to the travelers themselves. Push it to 99.9%, and the effect becomes even more extreme, with the dilation factor climbing above 22, meaning the crew would experience less than 3 weeks of subjective time for what observers on Earth would measure as over a year. This creates a genuinely fascinating and somewhat unsettling scenario for any hypothetical interstellar mission. Astronauts traveling at these kinds of speeds across genuinely vast distances, say tens or even hundreds of light years, could theoretically experience relatively modest amounts of subjective time, potentially just years or even months, while everyone and everything they left behind on Earth would age by decades, centuries, or longer. This is sometimes referred to as the twin paradox, a classic thought experiment where one twin stays on Earth while the other travels near light speed and returns to find their sibling, has aged dramatically more than they have. The problem, of course, and this is the crucial catch that tends to get lost in the more romantic science fiction portrayals of this phenomenon, is that achieving speeds anywhere close to these percentages of light speed remains almost entirely theoretical given our current propulsion technology. We've talked at length about the propulsion concepts being researched today: laser sails, nuclear thermal engines, theoretical fusion drives, but even the most optimistic projections for these technologies top out around 10 to 20% the speed of light for extremely lightweight, unmanned probes. Getting anywhere near the 90% range, where time dilation effects become dramatically significant, would require propulsion technology so far beyond anything currently on any serious drawing board that it remains firmly in speculative territory. There's also a sobering practical consideration buried in all this relativistic elegance. Even if we did develop a spacecraft capable of reaching these speeds, the energy requirements alone would be staggering. As an object approaches the speed of light, its relativistic mass, effectively how much energy would be needed to continue accelerating it, increases dramatically according to the same Lorentz factor governing time dilation. This is precisely why physicists consistently emphasize that reaching light speed itself is fundamentally impossible for anything with mass, since it would require an infinite amount of energy input as you approach that final unreachable threshold. Getting close to light speed, even at 90 or 95%, already demands energy levels that dwarf anything humanity currently has the capacity to produce or store. So while time dilation offers a genuinely fascinating theoretical pathway for shortening the subjective experience of interstellar travel, it's not really a shortcut in any practical sense. It doesn't make the journey easier, cheaper, or safer. It just changes how the passage of time feels differently for those making the journey versus those who stayed behind, which raises its own set of profound psychological and social questions we haven't even touched on yet. Questions about what it would mean to return from a journey to find that everyone you knew has aged decades beyond you, or has passed away entirely during your voyage. That's actually a perfect thread to pick up next, because the psychological toll of interstellar travel, separate entirely from the physics and engineering challenges, represents another dimension of this problem that deserves serious, honest exploration. Let's talk honestly now about something that often gets glossed over in the excitement around interstellar propulsion concepts: the psychological and emotional toll that a journey like this would place on actual human beings. Because no matter how elegant the physics or how advanced the engineering becomes, at the end of the day, someone, or more likely generations of someones, would actually have to live through this experience, and I think that deserves real, serious attention. Let's start with what we already know from existing spaceflight research, since even relatively short duration missions have revealed significant psychological challenges that scale up dramatically when you start imagining multi-year or multi-decade journeys. NASA and other space agencies have studied astronaut mental health extensively, particularly through long-duration missions aboard the International Space Station, where astronauts typically spend anywhere from 6 months to just over a year in orbit. Even within that relatively contained time frame, researchers have documented consistent patterns of psychological strain, including increased irritability, sleep disturbances, symptoms resembling depression and anxiety, and something researchers often refer to as third-quarter phenomenon, a documented dip in morale and motivation that tends to occur roughly 2/3 of the way through long isolation periods, well before the relief of an approaching return home kicks in psychologically. Now imagine scaling that up to a journey lasting not months, but years, decades, or in the case of true interstellar travel using currently realistic propulsion timelines, potentially centuries. If we're talking about a generation ship concept, where the original crew who launched the mission will never actually arrive at the destination themselves, and instead their children, grandchildren, or great-grandchildren would be the ones to finally complete the journey. We're introducing psychological and sociological challenges that go far beyond anything modern spaceflight psychology has ever had to grapple with. Consider the sheer strangeness of being born aboard a spacecraft, living your entire life within a closed, artificial environment, knowing that Earth is a place you'll never actually see except through historical records and stories passed down from your ancestors. Researchers who've studied this concept theoretically, including sociologists and psychologists who've written specifically about generation ship scenarios, have raised serious concerns about long-term psychological stability across multiple generations confined to an artificial, closed environment. Questions like, how do you maintain meaningful cultural continuity, shared purpose, and mental health across generations who've never experienced life outside a spacecraft? How do you prevent the gradual erosion of institutional knowledge, scientific literacy, or even basic technical skills needed to maintain the ship itself, especially as the why behind the mission becomes more abstract and distant with each passing generation? There's actually a term that gets used in some of this research, generation ship drift, referring to the theoretical risk that the original mission's purpose, motivation, and cultural cohesion could gradually erode over successive generations, potentially resulting in social breakdown, loss of critical technical skills, or even complete abandonment of the original mission goals by descendants who never chose to be part of this journey in the first place and might reasonably resent having been born into it without any say in the matter. That last point deserves particular attention, honestly, because it raises a genuinely difficult ethical question that doesn't get discussed nearly enough. Is it ethical to have children who will be born, live, and potentially die aboard a spacecraft, having never had any choice in that fundamental life circumstance? This isn't just a hypothetical philosophical exercise, it's something bioethicists and space policy researchers have written seriously about, drawing parallels to broader debates about the ethics of bringing children into difficult or constrained circumstances without their consent, but scaled up to an entirely unprecedented context. Some researchers have proposed potential mitigations for these psychological and social risks. Things like designing generation ships with deliberately diverse, robust cultural and educational systems specifically intended to maintain multi-generational cohesion, creating built-in mechanisms for democratic decision-making so that later generations retain genuine agency over mission decisions rather than being locked into choices made by ancestors who died centuries earlier, and even incorporating extensive historical and cultural preservation systems designed to keep Earth's history, art, and collective memory alive and meaningful across generations who will never set foot there themselves. There's also been serious discussion about alternative approaches that could avoid multi-generational crewed missions entirely, at least for the initial phases of interstellar exploration. This is actually part of why robotic and AI-driven precursor missions, like the tiny probes envisioned by breakthrough Starshot, are considered such an important stepping stone. Sending intelligent, autonomous probes ahead of any human mission allows us to gather crucial data about potentially habitable systems, verify that a destination is actually worth the tremendous human cost of a generation ship voyage, and even potentially establish preliminary infrastructure or resources before committing actual human lives to a multi-generational journey with no possibility of turning back partway through. And that brings up another approach worth mentioning here, the concept of suspended animation or induced hibernation for interstellar crews, an idea that sounds like pure science fiction, but has actually received some serious scientific attention in recent years. NASA has funded early-stage research into torpor-inducing techniques, essentially medically induced states of significantly reduced metabolic activity, similar in some ways to hibernation seen in certain animal species, as a potential solution for reducing the psychological toll of long-duration spaceflight, minimizing resource consumption during transit, and potentially even reducing the radiation exposure risks we discussed earlier by keeping crew members in a more protected, low-activity state for the majority of a long journey. While torpor-based approaches remain firmly in early research stages, with significant unresolved questions about how to safely induce and reverse these states in humans for extended periods, they represent yet another example of how the human challenges of interstellar travel are receiving genuine scientific attention alongside the propulsion and engineering challenges we've already covered. So when we zoom back out and consider everything, the physics, the propulsion technology, the political and economic will required, and now these deeply human psychological and ethical dimensions, I think it becomes clear that interstellar travel isn't really one single problem waiting for one single breakthrough solution. It's an interconnected web of scientific, technological, political, and deeply human challenges, all of which need to be addressed, at least to some meaningful degree, before humanity could realistically consider sending anyone, or anything truly ambitious, across even a single light-year of space. Let's ground this conversation back in something more concrete, Josue, because up until now we've mostly talked about the single light-year benchmark as an abstract unit of measurement. But if we're actually thinking about interstellar travel as a real, eventual human ambition, it's worth asking, where would we actually go? What real star systems within a reasonable distance might realistically be worth the tremendous effort we've been discussing? The closest star system to our own, as most people know, is Alpha Centauri, located about 4 light-years away. This system actually contains 3 stars, Alpha Centauri A, Alpha Centauri B, and a smaller, dimmer red dwarf called Proxima Centauri, which is actually the closest individual star to our Sun at roughly 4 light-years away. Proxima Centauri gets a huge amount of attention in interstellar travel discussions because of one specific discovery made in 2016, an exoplanet called Proxima Centauri b, orbiting within what astronomers call the star's habitable zone, meaning the theoretical distance from a star where conditions could allow liquid water to exist on a planet's surface. Proxima Centauri b is roughly Earth-sized, and its discovery generated enormous excitement, precisely because it's simultaneously the closest known exoplanet to our solar system and sits within that tantalizing habitable zone. However, there are some significant complications worth understanding. Proxima Centauri, being a red dwarf star, is prone to intense stellar flares, far more violent and frequent than anything our own Sun produces. Some astronomers have raised serious doubts about whether a planet orbiting so closely to such a volatile star, which it must do to remain in the habitable zone given how dim red dwarfs are compared to our Sun, could actually maintain a stable atmosphere or protect any potential surface water from being stripped away by intense radiation and stellar wind over billions of years. Moving further out, another frequently discussed target is the TRAPPIST-1 system, located about 40 light-years away, considerably farther than Proxima Centauri, but still remarkably close on a galactic scale. What makes TRAPPIST-1 so extraordinary is that it hosts at least 7 known rocky, Earth-sized planets, with as many as 3 of them situated within the star's habitable zone. This is an unprecedented density of potentially habitable worlds in a single system, discovered in 2017 through a combination of ground-based and space telescope observations, and it remains one of the most intensely studied exoplanet systems, precisely because of that remarkable multiplicity of potentially habitable candidates. Similar concerns apply here, though. TRAPPIST-1 is also a red dwarf, meaning the same questions about stellar flare activity and atmospheric stability apply to its planets as well. Ongoing observations using the James Webb Space Telescope have actually been specifically targeting TRAPPIST-1 planets in recent years, attempting to characterize their atmospheres, or in some frustrating cases, confirming that certain planets in the system may have no substantial atmosphere at all, which would make them far less hospitable than initially hoped. Another commonly discussed target is the star system around Tau Ceti, located about 12 light-years away, a sun-like star that's been a target of interest for decades, partly because of its similarity to our own Sun in terms of size and stellar type, making it theoretically more stable and less prone to the flare activity that plagues red dwarf systems. Several candidate planets have been detected in Tau Ceti's system, though their exact nature and habitability remain considerably less certain compared to Proxima Centauri b or the TRAPPIST-1 planets. There's also Epsilon Eridani, roughly 10 light-years away, another younger, sun-like star system that's attracted attention for decades, partly because it's been featured prominently in science fiction, including as the fictional home system in several notable works, but also because it represents a genuinely interesting, relatively close target for future study, even though confirmed habitable planets there remain elusive so far. Now here's where I want to bring this back to the core question we've been exploring throughout this whole conversation. Even the closest of these systems, Proxima Centauri at 4 light-years, would require roughly 4 times the travel time we calculated for a single light-year, using any of the propulsion methods we've discussed. Using Voyager 1 current speed, we're talking about well over 70,000 years. Using a hypothetical laser sail probe reaching 20% light speed, something like breakthrough Starshot's most optimistic projections, we're still looking at over 20 years of travel time, plus additional years for any signal or data to make its way back to Earth given the finite speed of light itself. That's actually one of the most fascinating and underappreciated details when it comes to any potential future mission Josue. Even if we could build a spacecraft capable of reaching a nearby star system in a human timescale, we'd still be dealing with the finite speed of light, limiting how quickly we could ever receive information back from that mission. Any images, data, or messages transmitted from a probe reaching Proxima Centauri would still take over 4 years to reach Earth, simply because that's how long light itself takes to cross that distance, regardless of how quickly the spacecraft got there. This means for something like Breakthrough Starshot's proposed mission concept, even in the most optimistic scenario, we're potentially looking at a total timeline from launch to actually receiving useful scientific data back on Earth that stretches beyond 25 or even 30 years. And that's for the theoretically closest and most feasible interstellar target, using genuinely cutting-edge propulsion concepts currently being seriously researched. Since we've now mentioned several specific exoplanets discovered around nearby stars, it's worth taking a moment to explain how astronomers actually find and confirm these worlds in the first place, because the detection methods themselves are honestly almost as remarkable as the discoveries they've enabled. The most productive technique by far has been the transit method, which is exactly how most of the TRAPPIST-1 planets, along with thousands of other confirmed exoplanets, were originally identified. The basic principle is elegantly simple. If a planet's orbit happens to be aligned in such a way that it passes directly between its host star and our line of sight from Earth, it will cause a tiny, measurable dip in the star's observed brightness as it transits across the star's face. By measuring the size, depth, and regularity of these brightness dips, astronomers can determine a planet's approximate size, its orbital period, and by extension, its distance from its host star, which tells us whether it falls within that star's habitable zone. This transit method was the primary technique used by NASA's Kepler Space Telescope, which operated from 2009 to 2018 and single-handedly confirmed the existence of thousands of exoplanets, fundamentally transforming our understanding of how common planets actually are throughout the galaxy. Before Kepler, we genuinely didn't know whether planets were common or exceedingly rare cosmic occurrences. Kepler's data revealed that planets, including potentially rocky, Earth-sized worlds, appear to be remarkably common, essentially suggesting that most stars in our galaxy likely host at least one planet. The other major detection technique is called the radial velocity method, sometimes also referred to as the wobble method. This approach relies on detecting the subtle gravitational influence a planet exerts on its host star. As a planet orbits, its gravity causes the star itself to wobble very slightly, and this wobble creates a measurable shift in the star's light spectrum, alternating between being slightly stretched, called redshifted, and slightly compressed, called blue-shifted, as the star moves marginally away from and then toward Earth in response to the orbiting planet's gravitational pull. By precisely measuring these tiny spectral shifts, astronomers can calculate a planet's approximate mass and orbital characteristics, even without ever directly observing the planet transiting its star. Both of these methods have their limitations, though. The transit method only works effectively when a planet's orbital plane happens to align almost perfectly with our observational viewpoint from Earth, meaning we're likely missing countless planetary systems simply because their orbits aren't oriented in a way that produces visible transits from our vantage point. The radial velocity method tends to be most effective at detecting larger planets orbiting relatively close to their host stars, since these produce more significant gravitational wobble effects, meaning smaller, more distant Earth-like planets are inherently harder to detect using this technique alone. More recently, direct imaging has started to become viable for certain exoplanets, though this remains technically extraordinarily challenging given how incredibly faint a planet appears compared to the overwhelming brightness of its host star. The James Webb Space Telescope has made some genuinely exciting progress here, and it's specifically been used to directly image and analyze the atmospheric composition of several exoplanets, including some of the TRAPPIST-1 worlds we discussed, by studying how starlight filters through a planet's atmosphere as it transits, revealing chemical signatures like water vapor, carbon dioxide, or other potentially significant compounds present in that atmosphere. This atmospheric analysis capability represents one of the most exciting frontiers in current exoplanet research, because it moves us beyond simply detecting that a planet exists and toward actually understanding what conditions might be like on its surface. Scientists are specifically looking for what's sometimes called biosignatures, chemical combinations in a planet's atmosphere that would be difficult to explain without some kind of biological process actively maintaining them. Oxygen combined with methane being one frequently cited example, since that particular combination tends to break down relatively quickly without something continuously replenishing it. There's also growing anticipation around future telescope projects specifically designed to push these capabilities even further. NASA's proposed Habitable Worlds Observatory, still in early planning stages, is specifically being designed with the goal of directly imaging Earth-like planets around nearby Sun-like stars and analyzing their atmospheres for potential biosignatures, representing a significant leap beyond even James Webb's already impressive capabilities. All of this detection and characterization work matters enormously for our original question about interstellar travel, Josue, because it fundamentally shapes where we'd even want to send a mission in the first place. There's not much point investing the tremendous resources required for an interstellar voyage, whether that's a tiny robotic probe or some far more ambitious future crewed mission, without first having a reasonably confident sense of what we might actually find when we get there. This naturally brings us to a question that sits at the intersection of everything we've discussed so far: distance, travel time, and the search for potentially habitable worlds. If there's other intelligent life out there somewhere in the galaxy, why haven't we detected any clear evidence of it yet? This is often referred to as the Fermi paradox, named after physicist Enrico Fermi, who reportedly posed a version of this question somewhat casually during a lunchtime conversation with colleagues back in 1950, essentially asking, "Where is everybody?" The paradox arises from a fairly straightforward line of reasoning. Our galaxy alone contains an estimated 100 to 400 billion stars, and as we just discussed, current research suggests that planets, including potentially habitable ones, appear to be remarkably common throughout that stellar population. Given the sheer number of stars, the apparent commonality of planets, and the vast age of our galaxy, estimated at over 13 billion years, considerably older than our own solar system's roughly 4.6 billion years, it seems statistically plausible that intelligent civilizations should have arisen elsewhere, potentially with enough of a head start to have already developed interstellar travel capabilities and spread throughout at least some portion of the galaxy by now. Yet we've found no confirmed evidence of extraterrestrial technology, communication, or visitation, despite decades of active searching. This is where our conversation about distance and travel time actually becomes directly relevant to one of the most commonly proposed explanations for this apparent silence. Even if intelligent civilizations are relatively common throughout the galaxy, the staggering distances involved and the corresponding travel times we've been calculating throughout this entire conversation may simply make meaningful contact or colonization far rarer and slower than casual intuition might suggest. If even a single light year requires such enormous timeframes to cross using currently plausible propulsion technology, and our own galaxy spans roughly 100,000 light-years in diameter, the practical challenges of any civilization spreading widely, or even just successfully making contact with another civilization before both potentially rise and fall within a cosmically brief window, become almost overwhelming to properly comprehend. There's a related concept called the Great Filter, which proposes that there may be one or more extremely difficult evolutionary or technological thresholds that most potentially life-bearing planets fail to pass, whether that's the initial emergence of life itself, the jump from simple to complex life, the development of intelligence, or perhaps most relevantly to our conversation, the survival of a technological civilization long enough to actually develop interstellar travel capabilities before self-destruction or some other civilizational collapse occurs. Some researchers have speculated that surviving long enough as a stable, cooperative, technologically advanced civilization to actually build something like generation ships or advanced propulsion systems might itself represent one of the most significant filters of all. The search for extraterrestrial intelligence, commonly known as SETI, represents humanity's most organized effort to actually detect potential evidence of intelligent civilizations elsewhere, primarily by scanning the skies for unusual radio signals that might indicate artificial origin rather than natural astrophysical phenomena. SETI has been conducting various forms of this search since the 1960s, and while no confirmed extraterrestrial signal has ever been detected, the search continues using increasingly sophisticated technology, including recent efforts like the Breakthrough Listen project, which is actually part of the same broader Breakthrough Initiatives organization behind Breakthrough Starshot, the laser sail concept we discussed earlier. There's an interesting logical connection worth highlighting here, Josue. If interstellar travel truly is as difficult and time-consuming as our entire conversation has demonstrated, using any propulsion technology remotely close to what we can currently conceive of, then radio or laser-based communication actually represents a far more practical and efficient way for civilizations to potentially connect across interstellar distances, since electromagnetic signals travel at the actual speed of light itself, dramatically faster than any physical spacecraft could ever hope to achieve. This is part of why SETI has historically focused primarily on searching for signals rather than searching for physical evidence of visiting spacecraft. If you are still watching, make sure to subscribe to the channel and give this video a like. Your support means the world to me. Some researchers have also proposed that if advanced civilizations do exist, they may have deliberately concluded that physical interstellar travel simply isn't worth the tremendous resource investment we've discussed throughout this conversation, and may instead focus their efforts on communication, or even potentially on sending small autonomous probes similar in concept to Breakthrough Starshot, rather than attempting large-scale crewed exploration or colonization efforts. All of this ties back to our original question in a genuinely humbling way. The distance of a single light year, which already requires such extraordinary timeframes to cross using any propulsion method we've discussed, represents an absolutely minuscule fraction of the distances that would separate most stars and potential civilizations throughout our galaxy. It's a sobering reminder of just how vast, empty, and challenging interstellar space truly is, even before we start considering the added complexity of two separate civilizations needing to exist within a compatible technological and temporal window to ever actually make meaningful contact. After all this discussion of vast distances, sobering timelines, and the humbling scale of the challenge, let's shift towards something a bit more grounded and optimistic, Josue. What's actually happening right now, or in the near future, that represents genuine, tangible progress toward eventually making interstellar travel more feasible? The most immediately relevant project is Breakthrough Starshot itself, which we've referenced several times throughout this conversation. Announced in 2016 with backing from prominent figures including the late physicist Stephen Hawking and Russian entrepreneur Yuri Milner, the project's ambitious goal is to develop a fleet of extremely lightweight, wafer-sized probes called starships, each attached to a light sail only a few meters across, and propel them using an enormous ground-based laser array capable of accelerating these tiny probes to roughly 20% the speed of light within just a few minutes of sustained laser pushing. The engineering challenges here are genuinely immense and worth understanding honestly rather than glossing over. The laser array itself would need to generate an almost unimaginable amount of focused power and would require extraordinarily precise targeting to keep the laser beam focused on a sail that's rapidly accelerating away at increasing speed. The tiny probes themselves would need to survive the intense acceleration forces, along with potential collisions with interstellar dust particles at relativistic speeds, which even microscopic particles could seriously damage or destroy a probe traveling at such tremendous velocity. And then there's the challenge of actually capturing and transmitting useful scientific data back to Earth from a tiny probe with extremely limited power and communication capability from over 4 light-years away. Despite these substantial engineering hurdles, breakthrough Starshot represents a genuinely serious, scientifically grounded research effort rather than pure speculative fiction. With real funding, real engineering teams, and real incremental progress being made on component technologies like ultra-lightweight sail materials and laser array concepts. Whether it ultimately succeeds in reaching Proxima Centauri within our lifetimes remains genuinely uncertain, but the research itself is already producing valuable advances in areas like extremely thin, reflective materials and high-power laser array technology that could have applications well beyond just this specific interstellar mission concept. There's also NASA's continued interest in advanced propulsion research more broadly, including ongoing theoretical and early experimental work on concepts like nuclear thermal propulsion and nuclear electric propulsion, which, while not nearly fast enough for interstellar travel, could dramatically improve travel times within our own solar system, potentially cutting a crewed mission to Mars down from many months to a matter of weeks in some proposed designs. This kind of research matters for our broader conversation because advances in nuclear propulsion technology developed for interplanetary use often lay important technical groundwork that could eventually inform more ambitious interstellar propulsion concepts down the road. Beyond specific propulsion technology, there's also been serious, sustained academic interest in the broader feasibility question of interstellar travel through organizations like the Tau Zero Foundation and various university-affiliated research groups, which specifically study concepts like generation ships, long-duration life support systems, and the sociological and psychological challenges of multi-generational space travel that we touched on earlier in our conversation. This research tends to be less about any single specific mission and more about establishing the theoretical groundwork and identifying which technologies would need the most development before any serious interstellar mission, whether robotic or crewed, could become genuinely viable. It's also worth mentioning, Josue, that some of the most important progress toward eventual interstellar capability might not come from headline-grabbing interstellar-specific projects at all, but rather from steady, incremental advances in adjacent fields, materials science producing lighter and stronger spacecraft components, advances in autonomous artificial intelligence systems that could allow a probe to make independent decisions during a multi-decade mission without needing constant guidance from Earth, given the communication delays we discussed earlier, and continued improvements in miniaturization, allowing more scientific instrumentation to be packed into smaller, lighter probes that require less energy to accelerate to meaningful speeds. All of this suggests that while we're genuinely nowhere close to solving the fundamental challenge our entire conversation has been built around, meaning the enormous timeframes required to cross even a single light year, there is real, active, credible scientific and engineering work happening right now that's gradually chipping away at the edges of this problem, incrementally improving our theoretical and practical capabilities in ways that could eventually make missions like breakthrough Starshot or something similar genuinely achievable within perhaps this century or the next. After all this discussion of real technologies and concrete projects, it's worth dedicating a moment to the more speculative theoretical physics concepts that occasionally get proposed as potential shortcuts around this entire distance problem we've been discussing throughout this conversation. I'm talking about things like wormholes and warp drives. Let's start with wormholes. Theoretically, a wormhole would be a kind of tunnel or bridge connecting two distant points in space-time, allowing, in principle, travel across enormous distances almost instantaneously without actually needing to cross the space in between. The idea comes directly from Einstein's general relativity equations, which mathematically permit solutions of this type, known as Einstein-Rosen bridges. The problem is that, although wormholes are mathematically allowed by the equations, nothing in known physics suggests they actually exist in nature, let alone that they'd be stable enough to allow anything to pass through them. Most theoretical models suggest that even if a wormhole existed naturally, it would collapse almost instantly unless held open by some kind of exotic matter with rather strange properties, like negative energy density, something that has never been observed or proven to exist. The concept of a warp drive, popularized by science fiction but also studied seriously by some physicists, is perhaps even more interesting from a theoretical standpoint. The best-known proposal is the so-called Alcubierre metric, proposed by Mexican physicist Miguel Alcubierre in 1994. Instead of the ship moving through space faster than light, which relativity strictly forbids, the proposal is that space-time itself would be distorted, contracting in front of the ship and expanding behind it, creating a kind of bubble that moves along with the ship. Inside this bubble, the ship would remain essentially stationary relative to local space, even though the bubble as a whole could move faster than light relative to an outside observer. The crucial detail here, Josue, is that this solution, just like wormholes, requires absurd amounts of negative energy or exotic matter to work, something we simply don't know exists in any usable form. Even if it did exist, estimates for the energy needed to create a warp bubble large enough to transport a ship reach values astronomically larger than all the energy available in our entire solar system, or even the entire galaxy. Depending on the specific model considered, some physicists continue refining these theoretical models, trying to reduce the energy requirements, and there have been genuine advances in this area over recent decades, drastically lowering the original energy estimates. But even these optimized versions still require amounts of energy completely outside the reach of any technology we can currently imagine, and they still depend on the existence of exotic matter with properties never experimentally observed. That's why it's important to be honest about the current status of these ideas. They're mathematically fascinating and represent a genuinely valuable intellectual exercise for exploring the limits of what physics allows theoretically, but they remain, for now, firmly in the realm of theoretical speculation without any known practical path toward becoming reality. This fundamentally distinguishes them from projects like Breakthrough Starshot, discussed in the previous part, which, despite being extremely challenging, is at least based entirely on well-established physics and technology that could, in principle, be developed through realistic incremental advances. That said, it's worth remembering that the history of science is full of ideas that seemed completely impossible until someone found an unexpected path forward. Still, based on everything we know today about physics, the most honest answer is that faster-than-light travel, whether through wormholes, warp drives, or any other proposed mechanism, remains extremely speculative territory, not something we should base realistic expectations on for interstellar travel in any foreseeable future. So after this long journey through physics, engineering, and speculation, it's time to finally answer the question that started this entire exploration. How long would it really take to travel 1 light year? The honest answer depends entirely on what technology we're talking about, and the range of possible answers is staggering. With today's fastest spacecraft, something like the Parker Solar Probe, reaching roughly 609,000 kilometers per hour at its fastest, it would take around 1,600 years to cover a single light year. With realistic near-future propulsion, advanced ion drives or nuclear thermal and electric engines, that number might shrink to a few centuries, still far beyond the span of any human life. With breakthrough Starshot-class technology, if it's ever truly achieved, reaching around 20% the speed of light, 1 light-year would take about 5 years. That's the most optimistic, realistic timeline discussed anywhere in this entire conversation. Push further into speculative, but still physically grounded territory, fusion propulsion or antimatter engines reaching 50 to 70% the speed of light, and the trip could shrink to somewhere between 1.5 and 2 years. And then there's the purely theoretical end of the spectrum, wormholes, warp drives, where the trip could, in principle, be nearly instantaneous. But as discussed, these remain firmly in the realm of unproven speculation, with no known practical path toward becoming reality. The core takeaway from everything covered across these 17 parts is this: 1 light-year, roughly 9 trillion kilometers, is such an incomprehensibly vast distance that even our fastest real-world technology would take over a millennium to cross it. Even the most optimistic near-future concepts still measure the journey in years, not days or hours. This is precisely why interstellar travel remains one of the greatest unsolved challenges in science and engineering, not for lack of ambition or imagination, but because the sheer scale of space itself imposes brutal, unforgiving constraints that no amount of clever engineering can fully escape without genuinely new physics. Still, it's worth closing on a note of real optimism rather than pure resignation. Genuine progress is happening through projects like breakthrough Starshot, steady advances in propulsion research, and continuous improvements in materials science and autonomous systems. Humanity has a long history of turning impossible into eventually achieved, even when it takes far longer than anyone initially hoped. So, to close the loop on the question that started it all, with today's technology, 1 light-year would take about 1,600 years. With realistic future technology within this century or the next, perhaps somewhere between 5 and 20 years. And with speculative physics that may never be realized, it could theoretically be instantaneous. But that's not an outcome worth waiting on. If you thought this journey through space and time was eye-opening, wait until you see what's waiting in this next one. Click the video on your screen right now and discover the real reason the stars might stay forever out of reach. Trust me, you don't want to miss this one.